Two types of customers, two types of servers. Customers of type 0 prefer servers of type 0, but will accept servers from servers of type 1 if they're the only ones available. Customers of type 1 prefer servers of type 1, but will accept servers from servers of type 0 if they're the only ones available. And then on the other side, if I'm a server of type 0 and there are type 0 customers awaiting, then that's the one that I want to process. But if there are none of the type 0, then I want to serve a type 1. Okay, so in other words, the customers prefer a server with the same label, and likewise the server prefers a customer of the same label, but are willing to work on the other one. So in terms of parameters, I mean that they were more or less defined for you. But the main thing is that the service times, and I know this is a little small, but the service times depend on both the customer and the server. In other words, for this model, you need to take that into account. See now, so the first problem is to formulate it without arguments. And then the second one, well, I said use only 3 events, and then the only way to do that is to use arguments. All right, so let's, oops, that was the wrong one. That is very weird. I keep selecting. I keep selecting the right one and it doesn't, it puts up the other one. I want this one, okay. Okay, so for doing it with no arguments, again, parameters fairly, I mean, you can still define the parameters and state variables as arrays, except that if we're not using arguments, then each event, you need a separate event for each possibility. Okay, so let's look at first principles here. Again, let's look at, say, Q0 and ask what possible changes to the state variable Q0 could occur. And I think almost everybody got this part. So we could have an arrival of a customer of type 0, and that would increment the number in Q, that is the variable Q0 by 1. Or we could have an arrival of a customer of type 1. Okay, so let's, now what I'm doing is, as suggested, let's skip over the scheduling edges for now. It's the next part where some of you kind of missed this. So let's look at Q0 again. What are the possible changes to Q0 that could occur? Okay, one is the arrival. What are the possible other changes? There are 2. One is that a customer of type 0 could start service on a server of type 0. That's 1. And that's this event here. But the second is that the customer of type 0 could start service using a server of type 1. And that's this one right here. And those are 2 different state transitions, because this state transition decrements the number of available servers of type 0. And this event decrements the number of servers of type 1. Those are 2 different state transitions. And so without arguments, you need 2 different events. And just in general, without arguments, if I have different combinations of states that I want to change at once, then I'm going to need an event for each one of those combinations. That's what we're saying again. For every combination of state transitions, I need a separate event if I'm not going to use arguments. And that's where I encourage you to start. In other words, when you're formulating something, it's often useful to just kind of start with lots and lots of events. And then, as we'll see in a little bit, to notice the patterns and see if maybe using an argument would be helpful. The thing is, and this is something where I actually have a bit of a disagreement with the guy who invented these event graphs, who is one of his motivations is he wanted to take event graphs that had lots of events and somehow collapse them into event graphs with fewer events. Many times that's actually a good thing, but in and of itself, it's not necessarily a bad thing. In other words, it doesn't cost any more, really, to define lots of events. What is costly in the execution are the number of events that are on the event list at any one time. So in principle, at any point in time, there's typically going to be, in this particular case, arrival events, and in this case, those arrival events are going to be in a separate component, but they're at any point in time, they're going to be two of them. You know, one for the arrival of customers of type 0 and one for the arrival of customers of type 1. Now, what you'll have the maximum number of events after some spinning, though, is going to be K0 times K0 end service 0 events and K1 end service 1 events. That's the maximum that will ever be on the event list at any one time in this particular case. And that's not really very many typically. Okay, so the same thing applies to the arrival of 1. We look at Q1, and what is it that could cause Q1 to go down? Well, first, it could start service on a server using a server of type 1. That's the start service 1.1 event. Or it could start service on a server of type 0, and that's this event, start service 1.0. And finally, now, I mean, and this is, when we look at the state variable, say S0, I mean, we've already counted 2 of the places where it could go down, and there aren't any other possible events that could cause it to decrease. So the only other possibility is for it to increase. And since there's only one S0 state, at least as a first cut, we only need one end service, or again, what we call them doesn't really matter. We only need one event to increment. So regardless of whether a type 0 server has been working on a type 0 customer or a type 1 customer, there's only one event that we need. Now, and I say as a first cut because sometimes as we're developing a model, an event graph model, it may turn out that at some point we may desire to split these. But you just have to be, at this point, it's not really necessary. And likewise for S1, there's similarly just what we've already had start service 01 and start service 11, which have decremented S1. And when does it increment? It increments at end service 1. And that's all we need. So there's nothing wrong with having more, but you just need to make sure when you do it, you realize that it isn't really necessary. Now, because we said for this that and I didn't really bother too much with it, but in terms of the run event now, we can just do everything, by brute force. So we initialize the Qs, we initialize the S's, and that's all we need. Okay, it's the scheduling where things get a little tricky. And it's the scheduling edges where we implement the preference of the customers for the servers and the servers for the customers. So the arrival events, the scheduling from the arrival events are what dictate the preference of the customers for the servers. And how is that done? Well, when a customer of type 0 arrives, then what this says is that if a server of type 0 is available, we will simply schedule a start service on a type 0 server. Okay, so what that means is I don't worry about anything else that's going on. Basically, this is the only condition that I need to schedule one. However, if what does the customer do if there's none of their preferred servers available, but there is some of the other type? Well, the problem description said that, that they would get service on them. In other words, even though the customer would prefer to be served by a type 0, they would accept service from a type 1. So this is how we express that. We say that if there are no type 0 servers and there's a type 1 server, at least one, then we schedule a start service where the customer is a type 0 and the server is a type 1. And the same thing for type 1s, except complementary. So a type 1 prefers a type 1 server. So if there's a type 1 server available, it will schedule a start service on that. And if it's not available, but there is a type 0, the one that's not preferred, then it will schedule on that. Okay, the something similar is going on for the end service. Well, the start service is fairly straightforward though. But again, say, look at this, like the start service on a type 0 customer using a type 0 server, the delay is TS00. And that's the delay in scheduling the end service. Likewise, if I start service using a customer of type 1 and a server of type 0, then it would be TS10. And the start service 01 would be TS01. And finally, if I start service on a customer of type 1, a server of type 1, the delay is TS11. So these are the 4 different service time generators. Okay, finally, what happens when a server of type 0 finishes service and is now available? Well, what that server prefers to do is to start service again on a type 0 customer. And it will do that only if there's a type 0 customer available. But if there's no type 0 customer available and there's a type 1 customer available in the queue, then the type 0 server will schedule a start service, and it's of a customer of type 1, but a server of type 0. And these need to be pointing to the right events. In other words, when I free up a server of type 0, I can't schedule any of these other two events because they are decrementing S1. They're decrementing a server, an available server of type 1, but I've freed up a server of type 0. So there's no guarantee. I mean, that just doesn't compute, basically. So similarly, for the end service of type 1, again, do the state transition, that because they prefer a customer of type 1, all it needs to do is check to see that there is an available customer of type 1. However, if there's no customer of type 1 available, but there is a type 0 available, they will schedule that event. And you need to make sure, see, here's the thing, particularly for any event that decreases a state variable that needs to stay non-zero, and that's true of all the Q's and S's that we've dealt with. In other words, I can't have a -1 in the Q. I can have 0 in the Q, but I can't have -1. And I can have no available servers, but I can't have negative available servers. That just doesn't compute. So what that means is that these start service events, as we've been calling them, all need to be absolutely assured that these state transitions can occur. In other words, if Q0 or S0 is 0 when this event occurs, then we got problems, because then we might wind up with -1 in the queue, which is, I mean, that has no meaning. Or -1 available servers. You know, I owe you a server. I mean, that doesn't compute. The conditions on the scheduling edges are what guarantee that, together with the state transitions. So let's look at this arrival 0 again. Okay, so it increments Q0. That means that Q0, after this event has occurred, has to be at least 1. And then the condition S0 bigger than 0 says that S0 now, in order to schedule this event, S0 has to be at least 1. And that guarantees that when this start service event occurs, that it will not lead to an inadmissible state. That is, Q or S will not go negative. Why? Q has to be positive, at least 1, because of the state transition. S has to be 1, at least 1, because of the condition. Likewise, on the other end, S0 has to be at least 1 because it's just been incremented. And this will only be scheduled if Q0 is bigger than 0. So between the condition and the state transition, there is a guarantee that this event will not lead to an inadmissible state. And similarly for this one. In other words, if we look here, so Q1 is at least 1, and S0 is at least 1, so that this state transition is always going to be legitimate. Likewise, if this is the state, if this is the condition, then S0 is always going to be at least 1 because of the state transition, and Q1 is always going to be at least 1 because of the edge condition. Okay, so if you missed on this, again, it would do you well to to look at what you had, and again, if you had any questions, and it may be, and it has happened, that I didn't understand what you were doing, what your event graph was about, and if you feel that's the case, always come and talk to me. Okay, what was the, okay. Now, the listener on this is where we have to use adapters. Well, or not have to is kind of strong, but the recommendation is to use adapters. So here, we need to use adapters because arrival 0, which is the name of the event, and arrival 1, which is the name of the event, neither one of those are scheduled by our arrival process. And so we adapt the arrival event from one instance of the arrival process to arrival 0. And so this will generate a series of arrival events, which will then be transmitted to server by calling it arrival 0. And that will in turn trigger these events. And similarly, the second one, adapts, changes arrival to arrival 1. So that's how the listener diagram should look. So a listener diagram includes adapters. And you know about all that now. Okay, this was a little bit more tricky. And I mean, so here's the motivation for this. If let's look back at this. First of all, it is kind of busy. I mean, it's not the busiest event graph that we'll encounter, but it's still a bit busy. It's not so much the busyness, but it's like, if we look at these two arrival events. So I have an arrival event called 0, and an arrival event called 1. And when I have an arrival 0, I increment Q0. And when I have an arrival 1, I increment Q1. So that kind of suggests that if I had a parameter, and our generic parameter we're calling I, then at the state transition, at least, I could always execute if you told me I using one event. And that's what's done here. If we just look at this arrival event. So now what's different is now I is an argument. And so, see, look at the difference here. Arrival with the argument I says increment Qi. So if I is 0, I increment Q0. If I is 1, I increment Q1. So that basically combines these two into one. And as long as I pass the right argument to it, it'll work. A similar thing, if we look at the end service event, we have a similar sort of thing. I have end service 0, which increments S0, and end service 1, which increments S1. And that just suggests that if I could put an argument there, that would tell me which one to increment. Now, just to avoid confusion, or a little bit of confusion, just by convention, I use J for the servers and I for the customers. Not necessary completely, although you have to be a little careful. But see, you see the end service event is one that I can combine the two end service events into one. And as long as I'm always past the correct argument, then it will work. Now, the more challenging one, let's look at the start service event. Here, there are 4 different possibilities. And so I need arguments that will consider all those different possibilities. Now here I'm calling it I and J. And I can be 0 or 1, J can be 0 or 1. So there are the 4 different possibilities. In words, this event says start service on a customer of type I using a server of type J. What are I and J? Well, somebody's going to have to tell me. Okay, so, but as long as you tell me what customer type it is and what server type it is, then this state transition will be correct. Okay, so that was kind of, That was kind of the straightforward part. Now, the trickier part has to do with scheduling. Okay, now how do I schedule them? The scheduling is what the real tricky parts were here. Okay, so there are, and here, this is a little bit of a trick, but when I have an arrival of customer of type I, whether that's 1 or 0, if, now this is SI, in other words, if the server of the same type is available, then I can schedule a start service passing it both I and I. In other words, let's look at the possibilities. If there is an arrival of type 0, meaning I is 0, and S0 is bigger than 0, meaning there's an available server of type 0, then I want to schedule, I'll schedule a start service on a customer of type 0 with a server of type 0. Likewise, if I is 1, meaning that there's an arrival of a customer of type 1. So I is 1, so S1 bigger than 0 says that is there a server of type 1 available? And if there is, I schedule start service passing I and I, in this case 1 and 1. So if an arrival of type 1 occurs and there's a server of type 1 available, then it schedules a start service passing 1 and 1. And when that start service occurs, it will decrement Q1 and decrement S1. All right, what about the other possibility? Well, the other possibility is that there is no server of the preferred type available, that is SI is equal to 0, but there is a server of the other type available. Now, there are kind of two approaches to this. One approach would require like 4 scheduling edges. Some of you did that. That was fine. The trick here is that you can flip between 0 and 1 by just taking 1 minus that. So let's look at that. Let's say we have an arrival of type 0. We increment Q, of course. If S0 is equal to 0, but S1 minus 0 is bigger than 0. So what's 1 minus 0? 1. So this says S0 is 0, meaning no type servers, 0 servers, but S1 is bigger than 0, meaning they're the other kind. Then I can schedule a start service. And what I'm passing is I, the customer type, and 1 minus I, the other server type. Okay, so now let's look at start service. Now, because you've told me what I and J are, I can now say TSIJ, because the event remember I said the event has to know these things. This start service event will not know which Q to decrement unless it's being told. And it's told because I is being passed in. Likewise, it doesn't know which element of the S array to decrement unless it's told. And here it's being told because it's being passed in. Finally, it doesn't know which service time generator to use unless you tell me both the customer and the server. But because I've passed in I and J, I can now just have one expression, TSIJ. Now remember, the end service event just has a single argument, J, which is the server that's completing service. And so that's all I need to pass in. I don't need to pass in the I. In fact, I can't pass in the I because there always needs to be a match between what's in the box, the parameter, and what's in the parentheses, the argument. There's a match here because there's a J and there's a I mean, it's not that there's a letter J, it's just there's one thing there. But the start service event, anything that schedules it has to give it two things. We already did that. So here we passed it two I's, but that's fine. It's not the name. See, arrival I doesn't have a J. It has no idea what J is, but it knows what I is. Okay, so there's something similar that happens here. In other words, if there's a customer of the same type that just finished service, the J, then you can schedule, and here's the condition for that, QJ bigger than 0. How does end service know which J to use? It's been passed in. But if that's the case, then it can schedule a start service using a customer of type J and a server of type J. In other words, the same. But if there isn't one of its own kind available, but there is one of the other kind available, then again, we can use the same trick as before. This should be flipped. That is, this should be I'll have to fix that. In other words, what's in the box should be 1 minus J and J. That's what should be in the box. Okay, I'll have to fix that. That's okay, but that's what's going on for this. Okay, now the last piece on this had to do with something of just a little bit different for the arrivals, and that there are a couple ways to do it. Conceptually, and again, you could do a subclass as well, but so here we have our basic arrival process. And the idea is that we have an arrival of type 0 with probability P. And let's see we had the probability that's a type 0 is P. And the way we do something like that is we have our parameter P, but then we also have a sequence of independent uniform 0, 1 random variates. So that when an arrival occurs, we sort of flip a coin. That is, we generate a U. If it's less than P, then we schedule an arrival passing it a 0. And if it's greater than or equal to P, then we pass it an arrival passing 1. That's one way to do it. An alternative would be, if you remember from your probability class, this would basically be a Bernoulli 1 minus P, meaning that X is 0 with probability P, and it's 1 with probability 1 minus P. And in that case, so if X is a sequence of these Bernoulli random variables, we just simply have to generate these X's, and that will schedule the right arrival. Okay, and then since we are scheduling arrivals with the right argument, we can now just use a straightforward listener. And since the same component is generating arrival 0s and arrival 1s, all we need to do is just hook it up to the server as a straight listener. We don't need to create more than one, and we don't need to do any adapting. Okay, so let's see. Can you see my NetBeans? I can't tell.
Yes, sir.
Yes, sir. We can see it.
All right, so instead of what I'd like to do is just show you how this is done, this last piece. Let's see, do I have time? I'm going to do them in reverse order, just so you can kind of see. So I'll this Bernoulli business may be me a little bit new, so let's I'll call it indexed arrival process because we're creating indices. And just to be lazy, I'm going to extend our arrival process. And okay, Bernoulli variate is a discrete random variate, and indexed process. And for some reason, the reason I do this is because of a NetBeans quirk where I need to put it after this, and I need to make sure it's private. Okay, so so that's my Bernoulli, and I, as is typical, I want to also have a master constructor. And then, oh, and I also need again, the names don't have to be the same, but yeah, just one thing I noticed in the last computer assignment is that some of you who, when you extended arrival process, would redefine the inter-arrival time generator as another instance variable, and that you don't do that because it already exists in the superclass, and so we can you don't want to. It turned out that it didn't really hurt anything, but it could. So just be careful of not to do that. Oops. Okay. So I just have time to test this one thing out. So let's see how that works. Okay, first, we define our inter-arrival time generator. And we use our random variate factory to get, let's have an exponential there. Oops. Okay. Okay, so the Bernoulli has, okay, so let's just to make them different. So we have a P of 1.4. And remember what, so we want a 0 with probability 0.4. And the thing about Bernoulli variates is that they generate ones with that probability. So we have to give it 1 minus that. Okay, so right, so why are we doing this so soon? Because I want to make sure that I've passed the parameters correctly. All right, so I can actually run it already and just make sure that I've gotten the right stuff. So I have here my Bernoulli variate. Notice that its P is 0.6 because that's the probability that it will give me a 1, and I want that. And then here's my exponential. So all right, so I've done that, and now again, no new state variables. All I'm doing is overriding do arrival. And I want to call the super one. And then let's int type is our Bernoulli variate generate int. So that's going to be either a 0 or 1. And I'll pass it the type. Oops. Wants me to add the override. Okay, so that's that override tag is always a very useful one. Okay, so what I'm doing is I'm saying that whenever arrival occurs, I'm going to generate the type and schedule an arrival passing that type. So what I'm going to see here is when I run it in verbose mode, it should give me. So let's stop on the event. Let's stop on 010 arrival events with an integer. Okay, so this is, and then I want to run it in verbose mode because I want to see those arrivals coming. And then I reset. I start simulation. And let's see what happens. Okay, so here's my run. And that schedules the first arrival. Okay, so here's an arrival. It schedules an arrival passing it a 1. All right, so now that happens. And here's another arrival. It's passing it another 1. Okay, here's another, this arrival is passing it a 0. And this arrival is passing, there it occurs. Now it's passing here another 1, another 0, another 0, etc. So you see that these arrival events with no arguments are scheduling arrivals that are either 0 or 1, and those can be passed to this arrival event. So I've implemented this way of doing it right here. Let's see, in 3 minutes, could I do this? Probably not. So I'll have to leave that as an exercise for the interested student. Okay, so I was going to do something else today, but I have run out of time. I hope this was helpful in terms of clarifying what is going on with these event graphs. I hope that the implementation kind of made it a little bit clearer what how we can use these discrete random variates, and in particular, I mean specifically, what one is, if you just look at these two different event graphs here, they both do exactly the same thing. They produce a sequence of arrival events with an argument that's either 0 or 1, and so therefore can be used to trigger this arrival event that has an argument on it. So, and there are two different ways of doing it. They're statistically equivalent, but they're different. And then the implementation, I didn't put it here, but the implementation didn't literally use the event graph as written, it's subclass the arrival process piece of it. Okay, so there are three, and I could have done each of these from scratch. And they're small enough so that it's not a big deal. But as I've constantly said, I'm lazy in that way, and so I'd rather just keep subclassing something that I've already implemented and tested.